some pizza for coming to this talk for the CSIP seminar this week. And for this week specifically, we have Dr. Zsolt Kollár, and he is currently a Fulbright Scholar in electrical engineering at Kennesaw State University. He's also an associate professor at the Budapest University of Technology and Economics, where he serves as the head of the MATLAB laboratory. Previously, he was a visiting researcher at Karlsruhe Institute of Technology, and he is responsible for the maintenance and development of the frequency domain identification MATLAB toolbox. And his research interest we will see today with his talk. So I will leave it to you. Thank you for coming once again.
Thank you. Thank you for the introduction. So, I said my name is Dr. Zsolt Kollár. I will be talking today about quantization noise. Usually when I start such talks, everybody gets frightened because I'm gonna do some probability theory and things like this. Don't worry, I'm gonna try to do an engineering approach. So basically, how you can deal in a digital system with quantity in the digital systems. And so yes, I'm the head of the MATLAB laboratory. That means we are doing close cooperation with MathWorks, and this is one of my topics. So what I really like to talk about. So I will have about 5 sections. First, I'm going to a little bit talk about quantization, but I think everybody is familiar with the term what it means quantization. So whenever I ask you, so what is the temperature? You might answer it's 74 Fahrenheit, or you say it's warm or cold. It's always you're not going to tell the 10 digits how big is how hot is the temperature. And then I'm going to talk a little bit about that's the basic quantization is the fixed point quantization. So whenever you have any type of neural network, it will be an interesting point. So usually you do your simulations in double precision or quadruple simulations. But actually, if you want to do the real implementation, you got to reduce the size of the numeric representation. So if you want to put in the FPGA, you might go down to a certain level. And the purpose of my talk is to give you an insight how you can handle these things and how you can actually predetermine how much noise you will have at the end of the calculations. And I will give you some perfect, so there will be some examples. I brought you 2 from the recent few years where we use these theories. And then I'm going to just give you a short summary and supporting material of what we developed in the last years. So let's start. So basically, whenever I have a signal, any type of signal, temperature, heart rate, anything you like, you will do quantization and sampling at both of the time. Why it's important? Probably if I talk about sampling, everybody knows the Shannon theory, Lycos theorem. So that's the easier part. I'm going to start with that because it's very important because the time domain sampling you can easily handle. Everybody knows you have the reconstruction filters and so on and so on. I will have just a few slides just to remember what we have. That we will do in the time domain. In the amplitude domain, we also have a quantization. That means there will be errors in this region as well. The question is that how can we handle it, and what do we have any restrictions similar like in the time domain? Just to rephrase that, in the time domain, so basically you have to sample the signal with twice as high frequency as the highest frequency inside the signal. This is the trivial. This is when you guys are at the signal processing group. So actually, this is the basics where we start from. The question is, what are the assumptions we have to make for the amplitude quantization? Or are there any restrictions to do that? The basic idea of this theory was developed by Professor Bernard Whitrow. The name might be familiar for you. He did developed the theory in 1954, and then it was extended by my father, Professor Zsolt Kollár. This will be the floating point in 2008. There's a book. Thank you for David Anderson. He lent me my book. I lent my book, my father's book. You can have a look. This whole book is about quantization noise. I don't want to frighten anybody. It's about 700 pages. There's a lot of theory inside, but I want to grasp on the engineering points. So what you can take out and what should be used for engineering approaches. Okay, but if you want to take a look at it, feel free. I'm going to put it here. Okay, so this 700 book deals with the amplitude quantization. So there's a lot to talk about. First of all, let's start with the basics. This is also probably known for both of you, also all of you. When you're dealing with numbers in computers, the most basic number representations are the fixed point representations, where you have a sign bit, you have an integer part, you have somewhere a digital point, decimal point, and then you have the fractional part. This is actually well known, so you can do the integer arithmetics. For most microcontrollers, this goes fast. And if you want to do an FPGA implementation, you might use this type of representation. The problem is with this type of representation is that you have a limited range for the numbers, and the numbers are equidistantly spaced. Okay, that's the restrictions you have with this type of number representations, and of course you have to deal with overflows and underflows. The object of the IEEE standard, this is the IEEE 754 2008 standard, it deals with floating point arithmetics, where you have a wider range, but of course the problem is that not all numbers are represented the same way. Okay, so you have an exponent and you have a fractional part, and this exponent tells you how you set up the number in the digital domain. Of course, usually you guys are probably working with some kind of machine learning, neural network, whatever. Usually you like to use double precision. But if you try your algorithm, I just dare you to try out your algorithm with half a precision or with single precision, it's not going to give you the same result. Some of you are nodding, so that's a good sign. But so basically, but actually the question is, can you predict the noise inside a system which uses floating point arithmetics? I think most of you who have seen just have any introduction to quantization noise, you know that the fixed point quantization that's easier to deal with. I'm going to show you how it deals with. You remember probably this quantization q squared divided by 12. That's the noise. I think these things are familiar for you. And then we're going to have a look at the floating point representation. What can we say about that? Okay. So these are the two topics I'm going to cover. First, the fixed point representation, then how you can take the same idea and use it for the floating point quantization. And what do you have to take away today? Okay, so let's start with the fixed point quantization. This is actually, I hope this is, again, usually they tell me when I'm talking about some topic, 40% should be known. And this is actually, I hope this is where I'm not going to lose you. So this is where you have the quantizer. So basically you have a quantization of the input amplitudes and you have the outputs. And usually this is actually a uniform quantizer, which means the gain is 1. And you see that every value is actually rounded to the nearest quantization point. Okay? And the representation is that, of course, the quantization noise is the difference between the quantized signal output and the input. Okay? As you might know, let's start with the sampling theory, and then because this will be an important part when we're dealing with quantization. So the sampling theory tells you that I'm taking samples from a signal in the time domain, and if I look at the frequency domain of signal, then the digital domain, you will have multiple copies of that spectral part. So that means that if you're holding the Nyquist theorem, you can set the signal using a low-pass filter of the digital signal. You have to just set it, and then based on these sample points, you will use a sinus x divided by x interpolation, and you can reconstruct the original signal from the sample signal, as long as, that's very important, so you know the Nyquist theory holds. Okay, that's where we start from. Now, this theory is nice, and we like it, but the question is, how can we apply the same thing to amplitude quantization? Is it even possible? Now, this is where it becomes tricky. So first, one more important term is the histogram, where I think that's also probably familiar to you. The histogram is actually telling you what is the relative frequency at a given value from the signal. So basically, if you ever take a random noise, the histogram is technically approximating your probability density function. And of course, if you start putting the quantization pin smaller and smaller, you will get close to this original analytical probability density function. Okay, so that's the basic theory behind the probability density function. This will be important because during sampling, we take samples from the time domain signal, and in the same time, we quantize the signal. And now what we're going to do is, instead of when we're looking at the sampling theory, it was done on the time domain signal. We are going to work for the quantization. We are going to work the same way, but instead of the amplitudes, we're going to work on the amplitude distribution function. So, as next step, just to understand. So basically, this was my quantizer. And if you look at the amplitude distribution, let's say we take a random noise with some limitations. And if you look at the each quantization bin, the area under this space will represent you the amount of the bin on that histogram. So basically, what we are doing when we are using a quantizer on the amplitude, we are doing a sampling of the probability density function, and we are actually doing a sampling and an area distribution. So what does that mean? That if you take a look at here, if we take the original amplitude distribution, we use here rectangular function for the integration on that between these bins, and at the end we will have a closely similar function as when we want to take the sample. So we have actually samples from the probability density function at those given points. Okay, but the thing is that instead of the amplitudes, we're going to use the amplitude distribution function. And these things, that's why it's going to be important. The sampling theory and the theory derived for quantization is very similar. So the same principles will be working for those both things. So again, so we took the amplitude distribution, we took a simple rectangular function, we multiplied it, and then we did the integration, and then at the end we have the samples of the amplitude distribution. So now we have to move. This is the only theoretical slide which will be more philosophical than technical. We have to take for each, I think for probability theory, you might be familiar with the characteristic function, which is the Fourier transform of the probability function of the amplitudes. So basically what we have to do is we have here if you take a Gaussian function, the Fourier transform of a Gaussian function, the Gaussian function, so that's not going to be different. The rectangular function will be a sinus x divided by x. And at the end, of course, we will have the same solution or the same problem, I think, as for the sampling theory. So basically, if we set our quantization bins according to the change of the amplitude distribution of the signal, we can easily, you see, we have taken samples here, and samples here from the amplitude distribution function. We can reconstruct close enough. You see, here was the original PDF was a sinus x divided by x, and the assumption, if we set the quantization bin small enough, we'll be able to reconstruct the signal as well. I'll just give you an example for this. This is a very nice way to see what happens if you have a histogram and you want to reconstruct the signal. So what you see here is the population in 1990 in the US. And this was done at each year. So for the given age, how many people lived at that time in the US in 1990. That means if you think about it, let's look at here. This was the original data with these bars. You see here, people in 1990, the people who were around here when were they born? Just out of curiosity, does anybody know about the US? When did the baby boom happen? After the war. Yes, that's the story about the make love not war. That really worked. So basically, you have here this pin over here. I just want to show you this pin here. This one here. This spike is actually right after the war when the people came home from the war. The other booms are actually, it lasted from 1945 until 1960, this baby boom. And this is actually a histogram of those values, so how many people lived in 1990. Now, what you see here is when you start taking larger bins for the histogram, you see this is actually with 5 years, this is with 10 years, this is with 20 years. So if you would have the population density sampled with larger quantums, what do you see in the approximated probability density function? That the theory, the same way the sampling theory holds in the frequency domain, the same way the amplitude distribution sampling holds, because if you look at it, this is actually a good upper mix approximation of the analytical function. You see, with taking the values of 5 years and 10 years, that still works pretty well. You see the fitted histogram is still good. But if your quantization is 20 years, look at the data, that's not anymore a good fit. So it's not going to be, it's like when you're doing an undersampling of the histogram. So what you will have to do about this is that whenever you have any type of signal, it's going to be very important in your system and also in your neural network, if you have to think about the system, what is the distribution of your signal? Because the quantization noise is a tricky signal because it's generated from the signal, but it's not correlated with the signal. Okay, so it's related to it, but in mathematical terms, it's not correlated. So based on this data, what's very important, that's what I really like about this theory from Professor Vito. He's still alive, he's 93 years old. I met him last month, and he's still working on some theory. So basically, this is what he derived, that the sampling and quantization are very similar things, but in different domains. So basically, the same principle as you had for the sampling has to be applicable for the quantization. You see here, of course, I'm not going to go with all these numbers, but you see that you take the t, that's the sampling time, and you have the q, that's the sampling in the amplitude quantization. Yeah. So basically, and you have the same type of theories, 1, 2, 3, and 4. I'm not going to talk about 3 and 4 because that's rough mathematics. But the basic idea is that as long as your sample signal is band limited and can be used to reconcile the signal, the quantization theory will hold. And now that's going to be very important. What is a quantization theory? So for uniform quantization, it's very easy. To model all this, we have done a lot of things, but at the end, we have one single result, that the quantizer can be said that it's actually a uniformly distributed noise at the output, and it can be modeled as a signal plus an uncorrelated noise with the variance of q squared over 12. This is the end result of all this theory, but it's actually, it holds very importantly, and that's what I told you. In mathematical terms, you take the signal and you take the noise, they are not correlated, so the covariance is 0. But technically, they are not. So in the engineering perspective, they are not independent because the quantizer generates the noise from the signal, but it's not correlated with it. Okay. So basically, what you can do is this is what I'm going to show you. Whenever you have a fixed point signal, so you have your neural network trained, you put it to a fixed point quantizer, you will be able to set up for every signal operation, because there are two types of operations whenever you're dealing with quantization noise. One of them is when you take the signal and you quantize it, that's the first step. And whenever you do any type of operation, addition, multiplication, subtraction, it's always the problem that the end result will be quantized at the end. So basically, you will have a noise. So until now, I think this is the easier part. That's when you say when you have a uniform quantizer, so you have a fixed point implementation. One more thing has to be also said, that whenever you're doing system, you have to take care when you're doing the calculations, you don't have an underflow and overflow, because that's an extra nonlinearity. Okay, but I will show you that different type of algorithms. So based on this result, this very simple result, you can derive, for example, the quantization noise in an FFT. So you can, in a closed formula, based on how many bits you have and how many stages or how many numbers of the points you have. So basically, this is the first result that's very important. That basically, if you're doing the quantization of the input signals amplitude distribution correctly, then these things hold. That means that the noise is uniformly distributed with the expected value of 0, and the noise is q squared over 12. Of course, if you start adding up such signals due to central limit theorem, you will have a Gaussian input, but always you can count on these noises. So that basically at the end, you were not able to determine the noise itself, but you can always determine some kind of momentum of the signal of the noise. Sorry. Okay, so it's going to be the end solution. So, but now let's think about a little bit on floating point quantization. I think this is where it might be, I hope this will be interesting for you and you might be able to apply it on your research. So, when you're using a floating point quantizer, the problem is the following, that small numbers are represented very precisely and large numbers are not so precisely. And also you have the problem that if you add a very big number to a very small number, you will get only the big number because you cannot, inside the floating point, you have this problem. So basically, the question is that how can you deal with such a system where you have floating point number representation, and what can you tell about the noise? This will be much interesting than the fixed point solution. So my question is that, does anybody have an idea on how to deal with such a quantizer? Because you see, it's not linear, so it's very hard to stack. How can you deal with it? And this is where it's going to be, the whole theory is going to be very simple. If you have an idea, and that's what, this was mostly my father's work. This is where he had the biggest idea. So actually, Professor Widrow developed the previous results for uniform quantization. So he set up these theories on the amplitude distribution functions. And then my father thought a lot about it, that how does this relate to the previous quantizer? So if you look at this one over here, this one, so how does this relate to this one?
You could naively just say whatever the maximum amplitude whatever the maximum numbers I'm gonna be like evaluating, and I can kind of just bound everything by that.
You can, if you look at the smaller region, that you can say that's linear. But let's say if you have a stretched value, what do you see on the how does this staircase relate to the first staircase?
Can you get a distribution or a function of the staircase size, and that function itself goes into?
Almost. The idea is much simpler than you think. This is, I'm going to show you, this is actually called, this is the amplitude distribution of the floating point quantization noise. It's called, well, my father called it the skyscraper distribution, which means that you have small errors with high probability and you have large errors with small probability. But the idea is how you can handle this whole thing is the following. This is where it becomes actually very unique. You say that you take a compressor function, and then the next step, what is this? This Q. This is a uniform quantizer. And then at the output of this value, you have an expander. So basically, you can use the theory derived previously and apply it for this uniform quantizer. The only extra stuff is that you have to have some kind of a theory for the compressor and the expander. It's just a nonlinear function, because that's what is doing the double precision also. So basically here you have a fixed point quantization with the same properties as previously. And at the end, this is where you can define the floating point quantization. So, basically, if you look at the input-output functions, using a nonlinear exponential, because technically a double variable is using an exponential, you have an exponential inside. So you have a compressor, which compresses the signal. Then you have a hidden quantizer, and then you have an expander at the output. Okay, this looks nice and easy, but actually, what is the result that you get from this? After a lot of mathematical, that's what I'm going to skip at the moment. And let's just analyze the followings. So I say that if the PQN model, what we have derived for the amplitude distribution, holds for the middle quantizer, what do you see in these two equations? And I'm going to explain this in another words. This is technically the quantization noise for floating point variables. What do you see in the previous case, in the uniform quantizer, you have the quantization noise was independent of, it was only dependent on the quantization pin. What is it dependent on in these two cases? I will tell you what's the difference and then. But this is exactly what you said, that you take a small area. That means that it's actually dependent on the input signal's power. So that if you have a larger signal, then the quantity noise will be also larger. Okay, for the fixed point, it doesn't matter on that sense. The difference between the two is the following, that if the hidden quantizer works as intended, then you can bound this quantization noise between actually 1/3 times 2 on the minus 2p, that's the mantissa, and 1/12 times 2 on the minus 2 times the power, the average power of the signal. The difference between these two lines, these are the main results of my father. The second line is precisely if the quantization theory also, so you set the bin size so small that the quantization theory holds for this one and this quantizer as well, the expander and the compressor, then you can actually state that you have the output variance is actually the noise of the signal is 0.18 times 2 on the minus 2 p, that's the mantissa, times the signal variance. So basically, you can set up your system and you can say, okay, I know the inputs of a certain, for example, neural network. You can say that the noise will be actually the number of bits used for the floating point. You can set up anything. It doesn't have to be a double, single, it can be anything else. And you have to say, you have to also know the input signals variance. Okay, and of course, still these things that the floating point noise and the signal covariance will be 0, so that's independent of each other. Okay. Now, so basically we have this result. So basically that will show you that there's a small, not actually small, but the big difference compared to floating point and uniform quantization. And in order to do that, I brought you two examples. So the first one is what I'm going to show you is basically the problem is the following. So let's have two signals. Both of them are real. Like, for example, you have two headsets, 2 ears left and right, audio channels, and you want to perform the FFT of the two signals in parallel. Okay, this is the most easiest thing. You say, okay, I take the first signal, these are real value signal, I use an FFT, I get the frequency domain components, second signal, another FFT, and I do this in parallel. But the FFT technically, as you might have known, it has complex inputs. So technically, you could be doing with some signal forming, you use a single FFT and you do a signal separation. You can do the same operations. The only thing is that instead of FFTs, you use some mathematical, you take advantage of the FFT's properties of the complex conjugate of the real value signal. And the second solution is that you can also do a subdivision and you can do an n divided by half FFT and you do a signal expansion, and so on and so on. So basically, you can have the same method. This is mathematically the same results. But my question is that before I show you the result and we discuss, what is your assumption? Which of these, in terms of fixed point implementation, which one would you use which results in the smallest quantization error? One thing that I would say that as a takeaway, usually if you can reduce the number of calculations in a system, that will reduce also the quantization noise. Okay, so basically, what do you assume which one will have the smallest quantization noise? Just out of engineering intuition. Let's make an educated guess. This I would say this is a conventional method. This is method one. This is actually doing some. You take the j times the other one, and you have to do some separation at the end. Here you have to do some subdivision, and then you have to do some multiplication with some harmonics. So which one do you think is going to have the smallest?
It should be the top.
The top is the conventional method. How would you do it? Brute force. But that takes two FFTs. So that means that the quantization noise is going to be related to the one single FFT. This one has only one FFT. The question is that the quantization noise introduced by this and this is smaller. Is it smaller than a single FFT? This one you have an n divided by half FFT, but you have a lot of calculations on the end. Okay, but let's have a look at it. What we'll have at the output. So these are the three methods, and I highlighted the smallest. The difference is not very big, but usually it can get big. So basically, method one, which takes only one single FFT, results for fixed point quantization. That's the smallest. We have also did the simulations. And for floating point, unbelievably, it's not the second one or the third one. It's the first one that produced you the best results. Why? What do you think? Why? What was, in case of floating point, what does the quantization noise depend on? The input power. And you see here, you form a signal which has twice as large power as the separate these and these. So basically, the results are corresponding what we're expecting. Of course, the results in these cases, you see it's not that big because here's a 0.72, here's a 1.44. So actually it's comparable, it's very small. Of course, if you go for higher ends, you will have a higher results for that part. Okay, so basically, this is why it's important when you're designing any type of system, a filter, an FFT, anything else. It's very important how you set up your simulations and how you set up your arithmetic steps. So if you do a division, you might think of it's most simplest example I usually tell the people. If you say that you want to add two numbers and then you want to divide, that's a good step. But you can also say, I take the first division, I take the second term, I divide and add up. Which one will result in a higher quantization noise?
First one.
Not the second one. The second one, because if you divide first and then add up, if you add up, addition doesn't result in direct quantization. If you do division, that's going to result. So basically, also the order of the operations can influence your quantization noise. Okay, but the problem is this whole theory is that what I'm only telling you is how much is the noise, the power to the noise ratio. Okay, I'm not telling anything about the noise. I only can tell you the noise power. That means that actually with this amount of power, my result will be different from the ideal. Okay, and this is why it's going to be very important also in neural networks. So when you go to single precision or half precision, based on this theory, you can apply it. Let me know if it can help you. We can easily apply these things, and then at the end we can calculate how much noise will be generated at the output compared to the ideal solution. This is what we have done. This is another example that I'm going to bring you, and you will see why is it so unique. So I'm also, besides quantization noise and signal processing, I do a lot of investigations in the direction of multi-carrier modulations, so 5G waveforms, and you might familiar with the concept of OFDM. OFDM is usually that's how LTE and all the digital television works. And basically, what you see here is there are some alternative solutions for multi-carrier systems, and basically, what's good about FBMC is called filter bank multi-carrier modulation. This is where I wrote my dissertation also in 2013. So basically, if you use, everything is nice because you see that the out of band radiation is about 100 decibels. That means that actually the signal is very narrow. And if you use double precision, you will see that actually you can reach about 120 minus 120 decibel suppression in the out of band leakages. But as soon as you have these, all the calculations were done in double. But as soon as if you put it on an FPGA and you start using fixed point implementation, this is what we tried out, and it works also. And we tried different implementation solutions. There are some with using polyphase filters and so on. And what you have to look at is this is the ideal case. This is a simulation in MATLAB, works nice. But as soon as you start with different bit lengths, you see if I instead of this double precision, I reduce the 64 bits to 16 bits. This is the red one. You already see I lose in the dynamic range. And again, if I go down to 12 bits, I lose. I'm already over there where OFDM is. So basically, if you go with the bit reduction, your system will degrade, because actually what happens when you start using smaller number of bits, your quantization noise level will be higher. And this will correspond, for example, in the spectrum of the signal, because this can be considered as a Gaussian or a uniform distributed noise. It's independent. Okay, it will elevate the error at the end. Okay, so based on these things, this is why I think we also derive some formulas for the receiver, where you can also set up the beta rate and you can calculate the quantization noise what is the minimum number of bits you require to reach a certain signal to noise ratio. Okay, so these analyses, I think the tool set what my father developed with Professor Vito and that we brought on are really unique and very useful. So you can actually, because how you have done it, probably you do extensive simulations, but without simulations, you can also do these analytically. So actually, we can also, I didn't show you here, but we have the analytical formulas and we actually can tell you how much will be the noise level of the quantization noise before we are doing any type of simulations, based on the number of carriers, based on the number of bits, and so on and so on. Okay, and last but not least, just a little bit of summary and supporting material. So if the topic was interesting for you, I think the book is somewhere over there, yes, that's a little bit tough. I wouldn't go jump into that, but if you're interested, I would highly recommend to look at my father's homepage. I actually am taking care of it. There's a lot of extra material. If you're using MATLAB, I think you are using either Python or MATLAB or some combination of the both for your research. There are toolboxes where you can try your neural network and try out what happens. That's what we are also investigating. So that if you were running on your PC and you have a double precision, everything is fine. But as soon as you reduce the number of bits to a single or to fixed point, you lose the accuracy. And this is where it's a tricky part. So what you can do. So this is actually the homepage. The theory was developed in 1994, but my father has a paper from 1996. That's the statistical theory of quantization. And the result of most of these work were the results of presented in that book at the end. Okay, but you have also toolboxes in the homepage. You just write me. I will gladly send you the material if you need for this quantization analysis. There are toolboxes both for fixed point and floating point toolboxes. Okay, so basically, and you can apply in my father's book, you will see a lot of examples on the control theory. So if you want to have because if you think about, if you have only a feed-forward system, the quantization noise will slowly add up. So if you do a lot of calculations, it will just add up. The problem, what is the problem if you have a feedback loop? What do you think?
Error propagation.
Error propagation, and the error will be actually getting higher and higher due to this feedback loop, and because the noise stays inside the system. Exactly, that's the extra stuff. Okay, so basically, what I wanted to just take away for you is that you can have for both fixed point and floating point quantization. The quantization noise can be handled as a separate noise. You can state the various statistical properties. For engineers, it's usually the mean value and the power. And usually you can set up all the equations for the power of any type of system, whatever you do in the calculations. And then at the end, you will have a closed loop, closed formula, depending on the various parameters of your system. Okay, and why is it important? Usually I tell my students that you give this example because if you ask you build up a nice Kalman filter, that's a very typical example what I usually bring out, and you go to the automobile industry and you ask them that I have a great algorithm for trajectory planning using Kalman filter, and what will they ask you? Does it fit into an 8-bit microcontroller? And because why is it important? Because they are manufacturing 1 million cars, maybe 10 million cars, and an 8-bit microcontroller costs $1. A 16-bit microcontroller costs $2 or $3. If you want to use double precision, that's gonna be maybe about $10. And they're just gonna ask you that, okay, can you fit it into an 8-bit microcontroller? If not, they're gonna use their good old least squares solution. Okay, so basically that's what's very important. And also in FPGA, if you're working with FPGA, the field programmable gate array solution with hardware, if you're using double precision, that will be a very cost inefficient solution, because if you're doing double calculations on the FPGA, that eats up all the resources inside. And if you have a small FPGA is a very costly resource as well. So this is actually for you, I would say the takeaway is mostly that if you're doing research, double precision works nice, but as soon as you get to the industry, they always ask that, okay, can you make it cheaper? How many bits can you lose? And each bit gives you actually depending on how much money, but how much money they can spare at the end. And this is what we are also doing in Hungary, that we are trying to develop algorithms, and we are trying to see if you start playing with these things on the number representation, how much money we can save, or can we put it into, can we get, we always in engineering you say, okay, you like to derive in the academic part, you like to derive lower limits. In engineering you just want to get under the certain limit, so there's no, you don't want to make it better or faster, you want to make it efficient and cheap. That's actually controversial always with your systems as well. Okay, so but as a takeaway, so actually the fixed point quantization easy, floating point quantization there, it depends on the signal power, but everything, as we have seen in my previous examples, it works very nicely. So you can get close formulas, and the simulations, I didn't put that slide in, but there are simulations you can have. There are some papers that we have wrote fit very well with these formulas, and also using my father's toolboxes. On this homepage you have the additional materials, you can simulate what you have calculated. So this is what we are currently doing. So we are doing some closed form formulas, and we're doing the simulations, and they fit very nicely. So actually the theory on uniform quantization and floating point quantization works very well. Okay, but of course, right now I haven't seen too many papers, but usually the approach is that people try it out with different number of bits, and then they compare the results. But you can actually, as I've shown you, you can actually do it on an analytical approach also. Okay, good. Thank you very much. That concludes my talk, and I'm open to questions.
Yes, thank you, Professor. So we don't have any written comments, but if anyone online speaks, we will hear you in the room, so you can unmute and speak if you want to. Of course, the people in the room right now are also welcome to ask questions. We have about 15 minutes, so there is plenty of time to ask some questions if you have them. Yes, Zsolt.
So I'm recently busy with image denoising, which is like a type of non-denoising, and I have tried conventional method and neural network. What I was actually nodding about using half precision and double precision is not just make it efficient, but usually image denoising better images, which makes the power of the input bigger.
Yes.
And then when we try to like remove that noise and have a better reconstruction of that noisy image, we have a problem and we stop at somewhere. And if we use half precision, it can't get any noise out of the image. It's literally useless. So I wanted like to explore ways to design filters that would maybe make us able to not use double precision and do not stop reducing that type of noise with a very big and like powerful input images. But nowadays, like the quality of images is like much higher than like 10 years ago.
Yes.
So did you investigate anything into design filters for neural networks?
Not in that sense, but what we have investigated, and that's where we could have a discussion afterwards, is the usage of dithering or some kind of, because that's what you're doing. Somehow you add up some noise to it. So that's also funny thing about quantization, that if you add dithering to a signal and then you do a rough quantization, sometimes you get better results, although you added some signal to some noise to the signal. But yeah, there we didn't do any, because I'm not an image processing guy, to be honest. We have done some simulations with dithering, but it's more on systems. But sure, we can have a talk and we can have a look at it. Sure.
Yeah, I think because it's like kind of very useful, and everyone who makes a cell phone or something like that, they are very interested in being able to picture from the camera.
Yeah, that's true. Yeah, but it's a similar concept. So actually, because if you use the quantization, because that's when you can reduce the data as much as possible in the compression, without losing quality. Yeah.
Thank you very much.
Yeah.
So you mentioned towards the end, and I also saw it was in beginning part of the book, what's it called? The table of contents in that book there. Dynamical systems are just anything with feedback, how quantization will accumulate and grow. Could you talk a little bit about that? Because maybe I'm just not understanding it, but intuitively I would imagine whatever error you sort of accumulate once you go back around, since it's uncorrelated to the signal itself, you're kind of always just whatever the output of your thing is, you're taking like random draws of these things that asymptotically go to normal distributions, right? You're adding up all these errors. Why does quantization noise?
Yeah, I'll give you an
accumulate
example.
instead of this average?
Are you familiar with the Zsolt filter?
No.
Okay, so the idea is that when you're doing some kind of let's say if you're doing an integration of one frequency, and let's say you have a throughput filter where the coefficient of A is you calculate something like 1, and the problem is that if you have a system where the poles, if it's on the, let's say it's marginally stable, that means your poles is, for example, on the unit circle. That's already a problem, because if you think about it, and you have a filter which has some poles on the unit circle, and the problem is that it will not be exactly on the unit circle, and if it's if it's outside the unit circle, exactly, if it's under. Yeah, so basically these things that you have to handle, these are IRR filters, of course, because if you have a field filter or an FFT, they are just single shot, so you just go through, no problem. So basically, in all systems where you have some feedback and it's not always exactly, so it's not always true. So if you have a moving average, that is not that critical, because you don't. But there could be also the implementation. So because how you would implement a moving average filter is that you have actually a field filter with the coefficients of 1 divided by n, and you feed it back and you add it up. And quantization technically happens when you add those two signals together. And that's where, so basically when you add up, you have an error, and then it comes back and again you have the error. So actually, exactly, so you're adding the noise to it step by step. So actually, exactly that's what happens. The noise will be growing constantly, thank you. Yeah. So basically, this is where, but it's not always the case. That's what I'm trying to. So it also depends on the design. So also with the signal processing steps, if you design it clever enough, you don't have this instability. But that's where I'm not giving you there's not a rule of thumb, but actually in the IRF filter, it's easier to have a quantization error which accumulates inside the system.
So it has something to do with the fact that not every system, but in systems where you're sort of on the verge of stability or whatever.
Yes.
Quantization can then.
And of course, if you have a double precision, you can run an IR filter forever, pretty much, and then the accumulation will be so small. But actually, if you run it long enough, it depends on you can calculate actually that part. We have done such simulations as well. And if you take like for example 8-bit approximation, then it will go pretty quickly.
Does this behavior vary for fixed point versus floating point? So I imagine floating point you have, I'm not sure if the benefit or
it's slower. It's slower. The effect is slower.
With catastrophic like cancellation, with big things, with small things, the small things don't contribute anything. Like
that's also this.
Whereas fixed point you wouldn't have that phenomenon. Does that help or hurt you?
Well, with floating point, you have the gain that the error of the accumulation is slower. So with the fixed point, you end up pretty quickly with an unstable algorithm, pretty quickly with an unstable position. That's the problem. So this is why it's very critical when you have an IIR system. It's always when you're doing audio signal processing, you run the system for some time, but you don't run it for forever. Because if you got to just reset the whole system and then just let it run again. Because if it's just a partial signal, that's not going to end up in a too big problem. But if you run it
long time over as time increases, then you accumulate.
Yeah, it's just the problem that I didn't talk about one more thing that plays a big role is that if you have a coefficient inside the system, which is that there is a quantization in the coefficient as well. That means that whenever you have a multiplication factor, which is, let's say, an extreme of it's pi, which you cannot represent, it's gonna affect, it's not gonna affect the noise variance, it's gonna offset the noise. So it's not gonna be a zero mean anymore, because so it's just an extra addition. So these things are, basically, this is where you guys are doing research, that's great. But this is where, when you have the algorithm, and you need to get an algorithm design engineer who thinks of these things, that, okay, what is my architecture? Is it FPGA? Is it microcontroller? Do I have a multiply and accumulate function, and so on and so on. So these are the things that really, when you just put your research into practice, that's the question you have to take, that, okay, can I put it in? Will it work?
Right.
And how much do I lose when I go out of my PC to the let's say,
Right, when the rubber meets the road, you actually deploy it.
yeah.
Instead of just working on math and doing some small simulations.
Yeah. But so these are things, and there are design ideas, of course, you can think about. So which ones, like I told you, which one you do the addition and then you do the division, and so on, because with the division you always lose bits. That's not always, but it's actually a solution. When you're adding constant values, then that's not going to be an issue. So
I don't know too much about this, but is this also a case where, like, I know the division for the longest time on like processors was hard, or at the very least there were multiple implementations. Are there like good division algorithms and bad division algorithms, or good division circuits?
I'll give you an example. There's the simplest one. If you can divide with I'll give you an example. So if you would have to divide a number by 14, about 14, and you don't really care about the precision, you would divide with 16. Because just cheat a little bit, and it's easier. Just that's the story. And it's there you have an error again. But these are things that's directly the implementation question, deployment. So where you can do the cheating. So why would you? This is actually the same story as why would you use FFTs with power of 2? Because you can easily implement. Yeah. If you say I will implement an FFT with 17 points, you kill yourself.
Weird.
Yeah, it's weird, and you don't do it. You say, okay, I'll do it with
or something.
with 46 and 48, and I don't care. So
so final thing, just because you brought it up, you talked about how, you know, a lot of times algorithms have these constants like pi or e or something baked in them, but of course we're using, you know, you can't represent transcendental numbers really with our hardware. So you have to truncate it in some way, and you said, okay, that sort of shifts the error either up or down or whatever. Is it, when you have these sort of systems where, like what we were talking about before with IIR filters or whatever, where you accumulate error over time, and those sort of things would then give sort of a constant push to the error one way or the other. Is there this maybe is out of scope, or just I don't know, but like with instead of using fixed values for say like pi or me, schemes where you would sample or somehow use whenever I need a call to use pi, sometimes I use pi a little smaller, a little bigger with some distribution of.
That's one approach that's very important. You brought it up. So that's one more approach that usually in systems you might end up with, also in FPGAs you might end up with mixed systems. So you have fixed point and you have floating point system where you need higher precision. I didn't brought that in, but in the FPMC system that I didn't give you the block diagrams because I don't want to fall into details, but that's what we also have done, that whenever you have a star system, we investigated which component brings the highest quantization noise to the table.
Right.
And then there you can say, okay, let's add 2 more bits there, and that's not going to be an issue for you at the end. So but yes, these are the questions that I'm not sure, have you done FPGA programming?
Not personally, no.
You know, it's a pain in the ass. So it's one because it takes a lot of time, and you have to do the wiring and a lot of. So it's one of the most. I have done this. It's one of the most time-consuming things I've ever seen, because it's just a lot of optimization, and then you have to put everything it's working at the end, and you're hoping for the best. It's not like in the compiler you can go for a coffee or maybe 2 hours, and then you have the results, and you have to check it, and it's just really hard. So that these things, and then what type of arithmetic units you have inside at your disposal. That's one more thing that if you I think you remember in the old days when I went to the university, it was in 2002. There were these digital design classes where we had to design everything with NAND gates because they were easy to depend. And they said, okay, let's design everything with NAND gates. And we had the nice Boolean algebra. And then, okay, they said, okay, sorry guys, we have only NAND gates, and design everything with NAND gates. And then we had these, I don't remember anymore, but I remember that I had the formula for the digital system, and then I had to design all this with I had the format that indicated, yeah, you remember this. Just because that was at that time available for the engineers.
Thing, it was,
Yeah, but that's so that's what I'm, so actually this is where it's a broad, it's not a broad place where you have your research, and then the question will be always that if you implement it, how bad is it gonna be?
Right.
So what do you lose?
But yeah.
And if you can quantize it, and you can tell me, okay, I can exactly tell you, so it's actually in this case, I can exactly tell you that, okay, this method is the best, use that. If you're using the same precision, of course. At the end.
And if things fit my modeling, yeah.
Yeah, you can do the modeling, and you can say, okay, this, but of course, there are a lot of things that I told you. So actually, what is the system you have, and what are the most, for the arithmetic units, what do you have, and also for what is even possible. So, because I also, if you think about it, currently, I think one more approach, what they are using is in a lot of systems, also in wideband system, is they are trying to use 1-bit quantizer, which is totally crazy, but it might be in some cases good enough,
Right.
and it's cheap.
I know a similar thing with like, I forget when Google talked about it, but they were, they use like TPUs for a lot of their machine learning AI stuff nowadays. And there was some paper that came out where it's like a lot of their stuff, they use 8-bit integer programming, like for everything. There's a floating point, it's all fixed point at the best. Even then, they're just like, they're weights. They don't need to be super accurate, just something.
Yeah, but the question is, where do you draw the line?
Right. Yeah. Well, obviously, at some point, you have to, quantization accumulation.
Yeah. So basically, that's the idea. So that you can basically quantization looks like very, for people who use statistics, no, it has a really engineering meaning. So you can apply it and it works. Of course, if you want to look at the background and statistics, that's why I didn't want to bring that. I brought you most of the results. Yeah. But that's what you have a 700-page book with all of theory. Yeah. Okay, good.
I have a question. So
yes,
I wonder if there's a way to sort of combat this noise, or is the philosophy more like choose enough bits so that the noise is small, or is there other?
Yes, that's the best. That's your suggestion is the best. Yeah. So one of them is that you say, okay, I need a signal to noise ratio of 60 dB. Then I need the best way to make sure you set up the bit size, but of course, this is where you have to start playing around. This is what I told you, for example, in this case, that mathematically, the question is, can you rearrange some things? So can you rearrange the math? And if you're able to rearrange the math somehow, you got to think about it. So, and also one more thing that you might want to think about is dithering. That's also you add additional noise, which actually improves the end results, which is totally dithering is a very crazy phenomenon, but it's an interesting phenomenon. But these things are actually if you have already good results, that's perfect. That's where you have to start thinking that maybe you can shift some things around, maybe you can reduce somewhere some steps, or maybe some reformulated, and those things might affect the quantization noise. But the most straightforward suggestion is exactly what you told me: increase the bit size. But that's what's good about this theory, that based on the bit size, you can actually estimate the noise power. Okay, but the problem is that it's only a noise. So basically, you might have larger and smaller power. So depending on the exact usage. And also one more important thing is that this theory, if I give you an example, if the input signal is a constant, this theory doesn't work, because if you have a constant, then your quantizer will always have the constant value. So you have technically you just have one value as an error. So it's very important that your distribution. That's why I told you the distribution should be for sinus, triangle. You have these are the basic signals. For Gaussian, for uniform distribution inputs, this theory holds pretty well.
It's almost
Sorry, I don't want to cut anyone off or anything, and you can continue the conversation if you want, but it is past time.
Oh, sorry, yeah.
And yeah, so I just want to thank you again for coming and thank you for presenting your work and having this great discussion. And if anyone online wants to reach you or reach your book or anything like that, I'm sure Professor Kollár would be willing to provide information, or if anyone online wants to email him, please do so.
Sure.
And yeah, so that concludes the CSIP seminar for this year. You were the last
Wow,
one of this
thank you.
year.
Yeah.
So yeah, we ended on a great note. So yeah, thank you again for coming. And yes, please reach out if you would like to speak to it. Yeah. All right.